Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Hello students, welcome back. In the last session we have started the basic concepts of the word computer architecture and organization, where we have learned about computer architecture, isn't it? So now computer architecture depends mostly on three major factors: the factors for instructions, data formats, and the addressing modes. In the last session we have seen the concept of addressing modes, where we have learned how to specify the data as an operand in an instruction. We have learned that data can be used directly, data can be used as a part of a register, data can be used with a location. Data can be used in a location, isn't it? So we have seen different ways of specifying data as an operand. And then we have seen the concept of data formats. In data formats, we have seen the ASCII format, the EBCDIC format, and the Unicode format. ASCII format is a 7-bit format where they were using 7-bit and an extra bit called as parity bit. So we had ASCII initially, and then we moved to a concept called as EBCDIC, where it is extended BCD interchange code. And then we move down to the next way called as Unicode, and Unicode is the mostly used data format in the present day world. It is the mostly used data format because it is of 16-bit in size. As it is 16-bit in size, the number of characters that we can handle is 2 power 16, that is 64k, which is 65,536 characters. So all the present day used languages have the characters, and those characters can be encoded using this 16-bit configuration. And that's for that. And now let us enter into the concept called as instructions. So what is the role of instruction? What is the role of the instruction in the computer architecture? As we have learned that computer architecture is basically the thing that gives you the logical functionality. It is a set of rules and regulations based on which you organize your physical components. Computer architecture never deals with physical components. Computer organization deals with the physical components, and computer architecture is all about how you handle things. It is the logical design or the blueprint or that gives the functionality about the components and the system flow. So coming to instructions, instruction is a word or a command given to a machine to make it work according to the user requirement, isn't it? So, and these instructions generally have two formats: the opcode is present, the operand is present. And along with this opcode and operand, few processors are designed to handle some flags, even flags. So based on which you design your programming, we make the control flow move ahead or move backward. So instructions are basically designed to have opcode and an operand. Right? This is a basic instruction format, and depending on the instruction format and the operands, we project two types of system architectures. So one is called as reduced instruction set computer, other one is called as complex instruction set computer. First one is called as reduced instruction set computer, and the second one is called as complex instruction set computer. So what are the basic differences found in these two things? And we got this classification of RISC, RISC and CISC, based on the instructions and the operands used. So in reduced instruction set computer, the mostly used operands are registers. There are no memory locations found in RISC. We work with registers only. In complex instruction set computer, the operand can be a register, the operand can be a memory location. It means that when the number of requirements grew, RISC was not enough. They started designing CISC based machines. In a CISC based machine, your operand can be a register, the operand can be a memory location. And in RISC, the operand is specifically designed to work with registers only. Fine. So basic thing is the storage unit registers, storage unit is registers as well as memory units. And as the storage unit is only registers, the number of instructions are less in RISC. The number of instructions are more in CISC. Why more? Because you can deal with memory locations, you can deal with registers also. As memory locations are also involved, the number of instructions also increase in CISC. And as we can use only registers here, we have less number of addressing modes in RISC and we have more number of addressing modes in CISC. RISC machines are less flexible when compared to CISC machines. RISC machines are less flexible or compatible when compared to CISC machines. They are less flexible because you can handle data that can be stored in registers only. As the register size and count is confined, you can handle up to a particular level of things only. Beyond that, you cannot use it. So these RISC based machines are less flexible when compared to the CISC based machines. So first one is the storage unit, second one is instruction, third one is addressing modes, next one is flexibility. Next is flexibility. So it stands for reduced instruction set computer. It stands for complex instruction set computer. The storage unit is registers here. It is registers as well as memory locations. Memory. The instruction count is less in RISC because you need to handle only register based instructions, and the number of instructions are more in complex instruction set computer because you need to handle data with respect to registers as well as memory. And coming to addressing modes, as the storage unit is only registers, we can specify data only in two ways, either data directly or data using registers. And as memory is also involved here, the number of addressing modes increase. Why do they increase? Because you can refer data directly, you can refer data with respect to registers, you can refer data with respect to memory locations also. And flexibility part, this is less flexible and this is more flexible. And coming to the speed of operation, the thing that makes RISC advantageous is, as RISC deals with registers, this has got a better speed compared to CISC based machines. Why better speed? Because as the data is found in registers and registers are a part of the processor can handle the data found in registers fastly when compared to the memory based things here. So compared to CISC, the speed of processing is a little more faster in RISC based machines. But the disadvantage is the number of operations are confined in RISC when compared to complex instruction set computer. And in RISC based machines, an instruction performs only a single operation at a single instance of time, and in CISC we can make the machine perform multiple operations in a single unit of time. Right with this? So this is the basic RISC based machines CISC based machines, and this has come into picture based on the instruction formats, right? So to write an instruction, you need opcode, you need operand, and to read the opcode, you should know the storage unit of that. So the storage unit is the deciding factor in designing the processor. Clear? So where the data is found, if that location is told, if that location is specified, then writing instructions becomes easy. So if you know where you can access data from, if that point is defined, then instructions can be framed. Okay, so the storage unit plays a major vital role in differentiating RISC based machines and CISC based machines. Fine. So we have three important factors. The factors were the instructions, the data formats, and the addressing modes. Is that fine? So these are the three basic factors using which a computer architecture is made to work. Now let us move forward to different types of computer architectures. What are the different types of computer architectures found? The first computer architecture found is Alan Turing architecture. The first architecture is the Alan Turing architecture. And then we have the Harvard architecture. And then we have the von Neumann architecture. And then we have multi-core architectures. And then we have Flint's architecture. And then we have Flint's architecture. So normally in colleges people speak about von Neumann architecture, but beyond that we should learn the basics of it, right? So when people started the thought of designing machines to make the machine work according to the user requirement, many great scientists and mathematicians have put their brain and heart and sweat in that. And the initial architecture that came into life was the Alan Turing architecture. In Alan Turing architecture, they were busily working with magnetic tapes and a storage drive, a storage box, a sliding box, which made that magnetic tape move according to the instructions. And this was a basic model of the computer architecture design. And what in reality people started implementing is the Harvard architecture. In this Harvard architecture, in the Harvard architecture, we have ALU here, we have control unit here, and we have memory unit here. And we have a separate memory space for instructions. We have a separate memory space for data. So this is basically the Harvard architecture, and the beauty of Harvard architecture is we have separate space for instructions to be stored and separate space for data to be stored internally, and you can handle instructions and data at the same time because you need to have them separate, right? So in this aspect you can handle them independently. But if you can write a program where you can handle the instructions and the data simultaneously, people call it as CPU. I wrote it as ALU. You can make it as CU. This will be ALU. Whatever, it doesn't make any big difference. So, and this was the Harvard architecture design, and this Harvard architecture is used in IBM based machines. And but even this was limited. This was even limited, and it was taking more cost per unit time because you can handle instructions part and data part independently. And after this Harvard architecture came into picture, then von Neumann designed a new architecture which is a modification of the Harvard architecture. Von Neumann designed a new architecture which is the modification of the Harvard architecture. And what did von Neumann design? So von Neumann designed this is IO, my mistake. That is IO part. The input, the output, and here we had ALU, and here we had CU, and here we have MU. If you observe this carefully, both are one the same. IO stands for input output in Harvard part, where I got input here and output here, isn't it fine? And this control unit ALU, and we have a single memory unit, and this single memory unit was common for both instructions, and it is the same for data. There is no separate slot for instructions and data in von Neumann architecture, and this is the mostly used architecture in the present day world. But the limitation is you cannot access instructions and data at the same time simultaneously. So that is a limitation to von Neumann architecture, and we call this as CPU. We call this as CPU. So the input comes to CPU. CPU is basically central processing unit which has got ALU, CU, MU involved in it, and this CU will generate the required control signals to make the instructions operate in a sequence. ALU is designed to perform all the arithmetic and logical unit operations, and memory unit is the physical memory unit which has got to store the program content and the operating systems part. So memory unit is found in common for both instructions as well as data in von Neumann, and this is where the limitation is found. In Harvard architecture, we have a separate memory slot. For instructions memory is separate, data memory is separate in Harvard part, whereas in von Neumann it's all put at one place, common memory. And people started observing that the processor designed has got a frequency of operation, clock pulses, and 8085 is designed to work with 3 megahertz. So if it is 3 megahertz, time period will be 1 by f. 1 by f would be 0.33 micro or 330 nanoseconds. So higher the frequency, lesser the time, because T and F are inversely proportional. So people started designing processors with larger frequencies. I mean, the speed of operation, to increase the speed of operation, the number of clock cycles have to be more. So T is 1 by F, right? So Frequency is number of cycles per second. In fact, so if 3 becomes 5, 1 by 5 is 0.2. If 3 becomes 10, 3 becomes 20. If mega becomes giga. So people started designing processors with larger frequency values. As the frequencies got up, as the frequency has increased, then we also had issues. We also had issues like the heating effect. And again, to minimize the heat, we are using heat sinks. So that became a big issue. So they thought instead of designing a processor with 4 gigahertz capacity, they want to divide that 4 into two parts. Like a single processor which can work with 2 gigahertz, they want to make it as two processors each with 1 gigahertz capacity. And they called each processor as a core, multi-core. So if you see your mobiles nowadays, people speak about dual core, quad core, hexa core, octa core. What is all these cores concept? What is all this cores concept? A core is an independent processor. You can think a core as an independent processor. So instead of designing one single processor with larger frequency of operation, they are dividing this single processor into multiple cores, core 1, core 2, core 3, and this is being divided into parts so that finally it's the same thing that works out. But the advantage is you can minimize the effects, the side effects what you get with a single processor. Because of this 2 gigahertz frequency, you need to design a larger heat sink. A larger fan is required that can cool the processor. Instead of having a single thing, they minimized it into multiple cores. When you have multiple cores, the cooling effect is lesser when compared to a single processor with larger frequency. Isn't that true? So what happens is, so as the cooling effect is minimized, you need not spend more on the heat sinks and the fan side. So today, people design multi-core architectures, and you observe that your phone becomes hot when you use it continuously. When you use it continuously, more amount of processor is being used. When the more amount of processor is being used, more heat is being developed. And when you charge it, also you find out, right? So things happen. So multi-cores are being designed. The application is designed in such a way that each core takes care of each functionality, and finally they put it all together to get the final output. So multi-core systems are being designed as a part of multi-core architecture. And coming to Flint's architecture, this is one important aspect which is used in the present day world. Flint's architecture is designed mainly for parallel system processing. When you want to design a machine for parallel computing part, people are using Flint's architecture, where Flint's architecture is made into 4 parts. Yep. SISD stands for single instruction, single data machines, single instruction, multiple data machines, multiple instruction, single data machines, multiple instruction, multiple data machines. And in SISD, SIMD, the basic components that we speak in Flints is CPU, the data, the memory. The CPU, the data unit, in fact. Okay. Coming to single instruction, and we call this as the processing element. You just copy it down. Please take it down carefully. Yeah. Coming to SISD, we have one control unit, one processing element, and we got single memory. Single memory. If it is single instruction, right? So one control unit, one processing element, but data is multiple, right? So we got modules. Now data is arranged in modules here. Single instruction, multiple data machines. And this SIMD is hypothetical. This is hypothetical. Because multiple instructions working on single data makes no big sense. Waste of time in designing MISD machines. And here comes the mostly used MIMD. So we have n control units, we have n processing elements, and we got n modules. So MIMD is the mostly used parallel computing architecture nowadays. So SISD, SIMD, MISD, MIMD. So please copy it down. Yes. So let us give a quick recap. Alan Turing machine architecture has got magnetic tapes and state box, and based on this state box we slide the magnetic tape to the required location. This was the basic initial architecture which was confined to very less number of operations. And then we have our Harvard architecture. In this Harvard architecture we have two memory spaces. One space is for instruction and the other space is for data, and you can simultaneously access instructions as well as data at the same time. And ALU is designed to handle with that, and control unit takes care of processing the instructions and data, right? Because you have two separate memory spaces, you can do it directly. But in this case the load is more on control unit because it becomes complex to process the things simultaneously. So then they moved forward, and then we have our von Neumann architecture. In von Neumann architecture, instead of two separate memory spaces, they designed a single memory space and they made a part of CPU and they call it as memory unit. And this memory unit is common for both instructions as well as data. Clear? And we will be learning about this memory unit where we speak about IO, shared IO, and memory shared IO. We'll be speaking about that IO space separately, but for the time unit take it as ALU, CU, and memory separately. Input and output. And then we have multi-core architectures. Up to von Neumann architectures we are using a single processor, and they started designing processors by integrating more components, and the frequency of operation was more F was used. But as the frequency got increased, the side effects got increased. As side effects got increased, one big effect is the heat being generated. So to minimize the heat, they were using some separate components like heat sinks and fans were used. So to minimize that, they started designing multi-core architectures. In multi-core architectures, the single processor functionality is divided into multiple cores. Each core can be thought of a single isolated independent unit which can function or work normally like a single processor. So a processor of 2 gigahertz is made into two cores, each with 1 gigahertz capacity. So as the load got distributed, the functionality becomes faster. As the core starts working simultaneously, the speed increases. As the speed increases and the load got distributed and the heating effect got minimized. So multi-core systems are mostly used in the present day things. And apart from this, to work with parallel computing, we need to develop, or we need to think about Flint's architecture. This Flint's architecture deals with instruction and data modules. So we have SISD, which stands for single instruction, single data module, SIMD, single instruction, multiple data machines, MISD and MIMD. So in a single instruction, we have a single control unit and a single processing element, and memory was also single. Coming to SIMD, we have a single control unit and a single processing unit. Control unit, processing unit depends on the instructions used. So single instruction, one control unit, one processing unit. As we have got multiple data things present, we use modules. And coming to MISD is hypothetical because designing a machine or designing an architecture based MISD based architecture is sheerly waste of time, because designing multiple processing elements, multiple control units on a single memory, single data devices is waste of things. For SD, SISD is good enough. So do not think of MISD. Now go beyond, call it as MIMD. In MIMD, we have n control units and we have what n processing elements, and these n processing elements work with n different modules. So this is how parallel computing has been designed by using Flint's architecture. And these are the various types of architectures that has been implemented right from day 1 to day n. Right? So and so moving ahead, uh, what are the basic things that makes an impact on the speed of operation? The basic things that make an impact on the speed of operation are as follows. The speed of operation can be given by, or the time, n into s by r. The basic funda that has been designed and taught is T is equal to n into s by r, where n is the number of instructions, n is the number of instructions, r is rate, s is number of stages per instruction. So when we speak about n times s over r, we have a concept called as time complexity and space complexity in your data structures. Leaving the side, when number of instructions are more, then the time taken to handle all those instructions will also be more. For example, time taken for each instruction, if it is 10 nanoseconds, two instructions will be 20 nano, 5 will be 50 nano, 10 will be 100 nanoseconds. So it is clear that as the number of instructions increase, the time taken also increases. So we observe that T is directly proportional to N. More the number of instructions being executed, more the value of T. And S indicates something called as number of stages. What do you mean by the word number of stages? The basic concept for every instruction to be told is whenever you are handling an instruction is handled in three phases. We fetch the instruction, we decode it, we execute it, we even store it. So we got four things. We fetch, we decode, we execute, we store. So in few machines we can speak about three stages, few machines we speak about four stages. So the number of stages again depend. So as the value of S is more, for example, if one instruction has 4 stages, 10 will have 40 stages, right? I mean, each stage will have some time being allocated. So time to fetch, time to decode, time to execute, time to store. We speak about two cycles called as fetch cycle and execution cycle. And these two cycles put together we call it as instruction cycle. So when you say the word fetch cycle, you need to fetch the instruction, then decode it, and the time taken to execute and store is called as execution cycle. So cycle is the time taken with respect to electronics and computer science. The word cycle indicates the time taken. So to handle an instruction, the time taken is given by the sum of fetch cycle and execution cycle. So we fetch, we decode, we execute, we store. So these are called as stages, and each instruction will have got its own stages. So as the value of S increases, the value of T also increases. And when you have multiple stages, and if they are independent to each other, we can implement a concept called as pipelining. With respect to these things. So more number of stages results in more time. And we have seen earlier that T and R vary inversely. As the rate of operation increase, the time taken decreases. Rate, the frequency taken, right? So more the F, lesser the T, right? So T and R vary inversely. So T depends on N, T depends on S directly, and T depends on R inversely. So putting all these things together, we get T is equal to N times S over R. Is that fine? And apart from this NSR, T depends even on the system-based softwares like the compilers used, the architecture used, the system architecture also makes an impact on these T. Clear? And we also speak about the number of hits happening. So we'll speak about the number of hits and the number of data miss when we speak about memory part, not for now. So the time taken depends on N, S, R. Apart from N, S, R, it also depends on the machine architecture, on what kind of machine you are working with. For example, if you implement a program on a i3 and on an i5, the same program on i3 processor and the same program on i5 processor, you will have definitely a change in time, because i3 functionalities, i5 functionalities differ, right? the speed is more. There are various factors. So based on the architecture used, we design the processors, right? So even architectures make a difference. So system architectures also have an impact on the time period, right? And along with that, we also speak about the system softwares. And this is how we speak about the basics of computer architecture. Fine. That's for now. Thank you.